This is my current 3-year-old multi-sensor. It was the first DIY electronics project I ever did with an ESP8266. And while it's been reliable, it does have some shortcomings. So it's time to look at building a better version with some upgraded components, and that's what I'm going to do today. So hang around. Hi, and welcome to Resin Chem Tech. In this video, I'm going to cover all of the current components of my multi-sensor, take a look at new components, test those, assemble them together into a new multi-sensor, and then put it out in the garage and see if it resolves some of the issues with the current version. I do expect it's going to be a rather lengthy video, so if there's any parts you wish to skip or you want to jump around, you can use the links here in the video timeline or down in the video description. The video description as well will contain links to all the parts that I use and a written version of this project that will include wiring diagrams and more. With that, let's get started. So the current multi-sensor out in the garage has sensors for temperature and humidity, motion, and light level. In addition, it has an RGB LED that can be used for a lot of things. I use it to indicate whether the alarm on the house is armed or disarmed. Now, the original intent of this device was to use the motion detector and light level to control my garage lighting, to basically have the lights come on when motion was detected. Well, while the light level has worked pretty well, the PIR sensor, not so much. But a lot of that has to do with my particular situation and my garage. To start, the range on the PIR motion sensor is only about 3 to 5 meters or 10 to 15, 16 feet. So right off the start, the range wasn't enough to reach the side service door. Next, I have an L shape or a tandem garage, so obviously no motion back here would be detected. So I thought I'd be smart and I would simply add a second standalone motion sensor to the back part of the garage. That should give me coverage of somewhere around this range. But I did find it was still too inconsistent when coming in and out of this service door, and eventually switched over to door sensors. I have a whole separate video on the garage lighting automation system, which I'll leave a link up at the top of the screen in the video description. But the idea was I would use the doors to turn the light off and on, but I would still use these PIR motion sensors to keep the lights on as long as motion was still being detected. So a PIR sensor basically uses something called passive infrared, and what it's doing is it's looking for a warm body in comparison to the ambient temperature around it, and that's how it detects motion. Now my garage happens to be attached to the house, but is neither heated nor cooled. So the garage can get very warm in the summer, and that causes a problem with these PIR sensors. As the garage gets warmer and warmer and closer to body temperature, the range gets shorter and shorter to the point that when it gets up above 90 degrees, I basically have to touch the PIR sensor to get it to detect motion. This is what I hope to fix with the new multi-sensor. So before we start building the new multi-sensor, let's take a look at the current multi-sensor, its components, and how it's put together to see if there might be other things we want to improve along the way in addition to that PIR sensor. So here's a little closer look at the inside. You can see that everything is done with jumper wires and pin headers, so this entire project was done with no soldering. Again, this was one of my very early projects, so most everything is just hot glue. Even the LED is inserted into DuPont jumpers. So we'll take a look at the individual components in a second, but this again is the first version that I built, and it was done following a YouTube video by someone. Channel's name goes by Bruh Automation. And it shows you how to create this version with no soldering. But we're going to improve upon this and see if we can replace a couple of components to deal with some of those nagging issues. These are the components that make up the current multi-sensor that's in the garage. We're using an ESP8266 Node MCU style for the controller. Talked about the PIR motion sensor, but it's an LM393. It is nice because it has a 5-second cooldown period, but it does have problems functioning well in higher temperatures. Speaking of temperature, I'm using a DHT22 sensor to report temperature and humidity. For light level, this is actually a photoresistor, but it's a photoresistor module. It is nice because it has an adjustment on here where we can adjust the light level to be detected. It's more or less a variable resistor. And we're using a common cathode RGB LED. Everything is powered by a 5-volt USB connection. And of course, everything is all put together with jumper wires and hot glue thrown together in just a generic project box that ends up having some holes cut in it and is just mounted on the wall. For the upgraded sensor, I'm going to stick with the ESP8266 node MCU. I might be able to drop down to a D1 Mini, but I think I'm going to need the extra pins, or I could go to an ESP32, but to be honest, ESP32 is really kind of overkill for this particular project. But the first thing we're going to do is we're going to replace this PIR sensor to try to take care of our temperature issue in the garage. Instead of using a PIR sensor, in this case, I'm going to use a microwave motion sensor. We'll take a little bit closer look at this, but one thing is this has a range of about 7 meters versus the 3 to 5 meters for the PIR sensor. In addition, it doesn't need any kind of opening since it's using microwave. Now, an interesting thing about this, and I'm going to test it, is we can adjust both the range for the motion and also the cool down time through the use of resistors and capacitors. So we'll take a little bit closer look at that, but it shouldn't have a problem with temperature of the garage being warm. Speaking of temperature, I'm also going to try replacing this DHT22 temperature and humidity sensor. The one thing I found when I compare this to multiple devices, I find that this always tends to run a couple of degrees warm on temperature and a couple percentages higher on humidity. Now I correct that through the sensor in Home Assistant, but in this case I'm going to try to use one of these, an AHT20 I2C temperature and humidity sensor. It's supposed to be quite a bit more accurate, so we're going to get rid of that and we're going to try using that instead. Now for my light level sensor, I could just use a standard photoresistor, and if I needed to adjust the sensitivity, add a resistor to that. I have an extra one of these, and I actually happen to like the fact that it has the variable setting here for the light level, so I'm probably going to go ahead and keep that, but you could just use a normal photoresistor and, if necessary, a standalone resistor. I'm also going to keep the common cathode RGB LED connector, but instead of using all of these DuPont connectors and the hot glue gun to connect everything together, we're going to get rid of that, and we're going to mount everything here on one of my favorites, an Electro Cookie prototype board, so everything will be soldered and secure. We will see if we can 3D print an enclosure as well. The current version of the sensor runs on ESPHome. We're going to keep ESPHome as the firmware for our controller as well. So that's the game plan, but I want to take a little closer look at both the microwave motion and this new temperature humidity sensor and do a little testing on both. Let's take a little closer look at this microwave motion detector before we start testing it. If we look down here at our pin headers, we will see our standard VN and our ground. Now this has an operating voltage range of 4 to 28 volts in, so we will need to run this off of 5 volts or 3.3 volts isn't going to work. You do see a 3V3 or 3.3 volt pin here. That actually is a 3.3 volts output that you could actually connect another device to, although I think it's only rated for somewhere around 100 milliamps. I won't be using that. Now you also see the CDS, and over here you'll see 2 pins for CDS. Now what that is used for is you can actually hook up a photoresistor to deactivate the motion detection above a certain light level. Or you might use this, let's say you want to use this to turn on a lamp at night, but you don't want the lamp to be turned on during the day. So by hooking up a photoresistor here, we can actually use light level to activate or deactivate the motion detector. Now in my particular case, I'm using door sensor to turn my lights off and on, and I'm only going to use the motion to keep the lights on if they're already on. So even though I'm going to have a light detector, I could put it here, but I'm actually going to use a separate light detector hooked to my node MCU. Wait, there's more. Let's flip this over and take a look at the back side of this. And we see some additional pads on here as well. Now the RCDS is where I can hook up a resistor, and now I can control at what level of light this is activated or deactivated. So again, between the CDS and this RCDS, I can use a photoresistor to activate or deactivate the motion. But there are a couple of other things on here. We'll see this RGN. What that does is that controls the range. I said by default that this has a maximum range of around 7 meters. We're going to test that. But if I want to shorten the distance, I can actually hook a resistor up to these two pads and control the maximum distance. Remember, as a microwave sensor, this is going to detect motion through the walls. So especially if I was using this to turn my lights off and on, I wouldn't want the garage lights to come on when someone walks by the outside of the garage or inside of the house. So I could actually shorten the distance by hooking up a resistor here. Also over here, we'll see a C-TM, 2 pins here. That is where we can hook up a capacitor, and we actually can control the signal time or that cooldown period. Again, by default, this is supposed to have a 2-second signal reset time, but by hooking up a capacitor, I can actually extend or make that time longer and extend a cooldown time. But before we actually hook this up and test it, let's take a look at some of the other devices we'll be using. This is the AHT20 temperature and humidity sensor. Now you can see it is quite a bit smaller than the DHT22 that I was using before, so it's nice that it's smaller. It's also supposed to be more accurate. If we take a look at the back of this, we'll see, again, we've got our VN and our ground, and this has incoming voltage range of anywhere from 2.0 to 5.5 volts. So we can run this off of either our 5 volt or our 3.3 volt line. And being an I2C device, it has 2 wires, a clock, and a data that will hook up to 2 pins on our Node MCU. Now, I do expect that I'm still going to have to mount this either externally or at least have an opening for the sensor here. The one thing that I found is that the Node MCU will actually generate some heat when it's running, and if I put this inside of a closed box with this, it is going to affect the temperature reading. So we'll see how that works out and if it's more accurate than the DHT22. Even though I'm going to use this same light detection sensor that I had in the old one, I did want to at least cover it briefly. Again, you can just use a standard photoresistor and another resistor. This obviously has a photoresistor on it, but this has a couple of advantages over that. For one, again, we'll see we've got our voltage in and our ground. This is 3.3 or 5 volt. It has an AO or an analog out pin, which is what I used before, and all that's going to do is give you an analog signal out in terms of light level, which you can easily convert over to lux or brightness, but it also has a DO or a digital out pin. And by using this small little potentiometer on here, we can set this to either be on or off based on a light level, again, which is adjusted with this. So you have the advantage using this module of using a digital out or an analog out. Last time I used the analog, this time I might try using the digital. I use this so that if you open the door to the garage, and let's say the overhead door is open, or there's already enough ambient light in there, it won't automatically turn on the garage lights. Again, I could have wired that into this, but I'm going to go ahead and use this separate sensor instead. While we're covering all the components, I might as well go ahead and cover this common cathode RGB LED. Now, if you're used to working with LED light strips like WS2812B, this is going to be a little bit different because in the case of a light strip, you normally send your 5 volts and you send a data signal. In this case, we've got 4 different leads here. The long one is going to be your ground. Then each one of these shorter pins is going to be your red, your green, and your blue. And we're going to hook those 3 up to 3 different pins on our Node MCU. And by bringing one of these pins higher, outputting 3.3 volts to each of these, we can turn on the individual LEDs, the red, the green, or the blue. Now this is rated for 3 to 3.2 volts, so technically you probably should add a resistor, although I've been running them and I tend to run it at a little less brightness through Home Assistant, and I haven't had any problems running it directly off the 3.3 volt pin. But you can use this for any kind of indicator that you want. And again, we can control that through ESPHome and through our automations. So next, I'm going to test each individual component before I assemble them into the full multi-sensor. Once again, if you're only interested in a particular device or just want to jump straight ahead to the final version, again, remember to use these time links here in the video timeline. First thing I want to test is this new microwave motion sensor. And I need to find out whether the current default range or distance and the timeout period or the signal time is going to work in my particular case. So what I've done is just thrown together a very simple breadboard. I've went ahead and soldered a couple of leads across those, so if I do need to try capacitors and resistors, I can easily swap them out to get what I need. I'm just running my Node MCU with a very simple Arduino sketch that all it's going to do is toggle this LED off and on based on when this senses motion. So I'm going to lay out a tape measure and see what kind of range it looks like we get by default without any resistors, and what our timeout period looks like with our default signal time. Okay, I've got the test rig set up here beside me, and you can see I've got a tape measure laid out on the floor. So at this point I'm only about 2 feet away. You can see it's obviously picking up motion there. So I'm going to walk out there, and you probably won't be able to hear me very well, but I'll try to give you some indications of how far away I am, and we'll keep an eye on this to watch it for to detect motion. Now I did repeat this test multiple times. I also tested off to the angles and off to the sides to see what that gave me. Now here at 15 feet, if you remember, is about the maximum distance from a PIR sensor. So anything better than that is obviously going to be an improvement. I did find that the sensitivity or the range was directly in front of the sensor itself was the best. Once I got up to 25 feet, pretty much didn't get any motion detection, but it was pretty consistent at right around that 22 to 23 feet, which is at the 7 meter advertised amount. Now I did occasionally get it to fire, again at 25 feet, but it really was pretty much consistent right at 22 to 23 feet. So if this is the current coverage map of what I have in the garage now using 2 PIR sensors, again under ideal conditions, what I ought to see with the new microwave sensor is coverage that looks something like this. Now we'll have to see how much the range is impacted by the walls over in this particular area, but I'm going to take a look at that towards the end of this video. So I don't think, in my case with the garage where I'm going to put this, I need to adjust the distance or the range at all. And as far as the timeout is concerned, it's a little bit hard to tell. It seems like this might be just slightly longer than the 2 seconds, but it's definitely going to be less than the 5 seconds. For me, I'm not going to need to make any adjustments to that timeout period as well. So I've gone ahead and I've removed those wires. But of course, if you do need to make adjustments, you could easily add a capacitor or resistor to change either the signal time or the detection distance. The one last thing I do want to try, however, is putting this inside an equivalent of what's going to be a 3D printed enclosure. So I want to throw that there over the top and kind of repeat my distance test to see if that's going to make any real difference in terms of whether it's going to affect the distance. Obviously here close, it's obviously still detecting motion through the box with no problem, but I'm going to walk back and also kind of repeat that distance test and see where it tends to stop detecting motion. So after I repeated all of those distance tests again, this time with that 3D printed enclosure in front of the sensor, I didn't notice any impact or any real change in terms of the range of motion detection. So now I want to move on to taking a look at that new temperature sensor. And to test our AHT20 temperature humidity sensor, what I've done is I've just flashed a different simple Arduino sketch to this. It's just going to report temperature and humidity from this every 30 seconds. I've got my 2 other external devices here, along with 2 DHT22s that are connected to Wemos D1 minis. It's not going to be real exciting to watch on video, so I'm going to let this equalize for about an hour, and then we'll compare all 5 readings to see how this agrees with the other devices. And after about an hour here, we can see the results. These are both sitting at 75.6, 75.7 with a humidity of 42%. Meanwhile, our DHT22s are reading 76.6 and 77.1 degrees Fahrenheit and 47% humidity. So again, about a full degree higher, and even a little bit more, about 1.5 degrees higher on temperature and about 5% higher on humidity. While our AHT20 is currently reading 75.7 and 44% humidity. So on the temperature, it's pretty much dead in agreement with these 2 devices, and it is about 2% higher on humidity, but it's definitely closer to these devices. Now, there's no guarantee that these are the most accurate, but in terms of the agreement, these 3 devices are all agreeing, while our DHT22s are tending to read higher in terms of both temperature and humidity. So this does seem to be a little bit more accurate, at least from this very unscientific test. And finally, I want to test the digital output pin on this photoresistor module, since before I used analog and had to go through conversion, when really all I'm interested in is the light above or below a certain level. So I've wired this up pretty much in the same way as I did for the motion detector. This is going to output a high or a low signal based on measurement of the light. And I'm going to turn this LED red when the light level is too high, and basically it would be shut off, and have it turn green when the light level drops low enough. So let me just plug this in. Okay, we can see right now there's too much ambient light, and so therefore my garage lights would not come on in this case. This is going to be a real easy test to do. I just simply have to cover this up, and we can see our LED turn green. Now, at which point my garage lights would come on and back to off. So that is definitely a lot better than using that analog signal. I definitely like this being a binary off and on, and much better. And again, once I get it in the garage, I can set that light level with this little potentiometer on here. Now that all the individual components have been tested, it's time to bring them all together on a single breadboard and test the multi-sensor. But before we do that, I've got to replace that Arduino test code on our Node MCU with the ESPHome code. Now, I'm not going to go through all of the ESPHome code just in the interest of time. I've got other videos that covers how to install ESPHome to your ESP8266. But there will be a copy of the ESPHome code in the written version of this project. Again, you can find a link to that down in the video description. Now we've got ESPHome flashed onto our Node MCU. It's time for one final breadboard test before we move everything over to the soldered version. And just a quick review, this is our motion detector. This is going to be our temperature and humidity. This is our light level. And while it's a little bit hard to see in all this wiring is the LED. Again, a copy of the actual wiring diagram will be available in my related blog article. So we're going to plug this into USB, and the first thing we hope is we don't see any magic blue smoke. But everything's working right. It should show up in Home Assistant for us to automatically onboard, and we should be able to see all of the devices. So let's plug this in. Okay. And so far everything looks good. We've got our blue indicator light on this, so now we need to go over and check Home Assistant. Well, in my infinite wisdom, I forgot to click the record button, but it did pop up showing that a new device was discovered. So it was an ESPHome device. I simply added it, and here is that new garage multi-sensor. So if we take a look at that, we can now see all of our different sensors are in there. There's our motion. If I wave my hand in front of that, we can see motion was detected. We've got our analog light level, our digital light level. Now my temperature is showing Celsius right now, so I will have to fix that. But let's also cover up our light sensor here. And yep, that turns on and off. So everything appears to be working with all of our sensors. So we're ready to move this to the final soldered version. Oh, and I should also test our LED here. So again, I turn that on. You can see the LED comes on and goes back off again. So that is working as well. So once again, in the interest of time, I'm not going to go through the step-by-step process of soldering these components onto the electro cookie board. You can refer to my wiring diagram if you want to see how I opted to make all the wiring connections. I will make a few comments along the way, however. This is the 3D printed enclosure that I ended up designing. Now, I'm not real good at 3D design. This was done with the free online Tinkercad, pretty much using squares and circles. But I will make a couple of notes about it. Down here at the bottom, you'll see these little feet or these offsets. That allows me to not only screw my electro cookie board into the enclosure, but since it's raised up, it gives me the ability to make wiring runs on both the top and the bottom side of the electro cookie board. It gives me a little bit more space and a little more flexibility in terms of how I want to run my wiring. And I mentioned this before, if you don't have access to a 3D printer, again, you can just use something like a plastic project box, which are easy to get off of Amazon. They come in different sizes. This one's actually kind of a good size for a Wemos D1 Mini. Or you can even use something like, well, I guess you really can't see that because it's green. Let me switch over here. Something like just a soap dish, things that you might be able to find at a dollar store or maybe at a flea market, anything like that can be an enclosure. It's pretty easy to drill or add holes to it. So again, don't be discouraged by some of these projects if you don't have a 3D printer. And I have everything mounted in the box, including our motion detector, and again, our light level sensor here on the side. And what I've done just for testing is I've gone ahead and done an automation within ESPHome itself that is going to turn this LED light on anytime motion is detected, and it'll turn the light back off when it clears. That is not the automation that I'll be using in Home Assistant when it's all said and done, But for right now, that's on there so that we can test the motion once I mount it in the garage. I've taken my old sensor down off the wall and I've put the new one up in the same spot. Now I've went ahead and adjusted the light level, and you may not be able to see this, but right now when there's ambient light in the garage, it basically disables the automated lighting system so the lights won't come on. When the light level drops, probably can't see that second light went off. Turn that back on. So that's already been adjusted, so when the overhead doors open, the overhead lighting won't come on. I've also went ahead and repurposed this back to my alarm system. Part of the reason why is I realized when I go around the corner, I'm not going to be able to see this. So I wasn't really going to be able to test because the most important part's around the corner and I wouldn't be able to see the indicator light. So here's what I've done instead. What I've done is I've temporarily repurposed my matrix clock, wrote a couple of quick automations in Home Assistant so that when motion is detected, it's going to tell me that the sensor is fired. And then when motion clears, it'll go back to all clear. So that way I can test this by moving around the garage and I'll be able to see that from anywhere, and it should show up a little bit better on the camera. I've also put tape on the floor at about that 23-foot mark. If you remember, that was kind of the maximum range. And if you kind of extrapolate that around, it should pretty much cover the entire garage. But I'm going to set the camera up on this tripod just outside of that tape and then move around the garage and give our sensor a test. Okay, I'm currently standing right here next to the camera and I'm just outside the range of that tape. So the first thing I want to do is kind of approach the sensor and see if we're still going to get about the same amount of range, and there we go. I'm actually standing just a little bit outside of the tape still, so I'm probably just a tad over 23 feet, but it is, again, reliably detecting motion right here at 23 feet. Next, I want to move over towards the service door. Okay, you probably can't see it, but the service door is actually located right behind me, and I'm just going to make a little bit, just the slightest bit of movement, and you can see that motion fired. So unlike even when I was using two PIR sensors, I could not get reliable motion detection here at this service door. And now it seems to very consistently be firing with even just the slightest bit of movement. But the area that I'm really most interested in is going to be back here in this corner. The cars are generally parked in this part of the garage, but I'll tend to come out here and do some work. And again, without being able to detect motion, what would happen is after 45 seconds, the lights would turn off on me and I'd have to yell at Google to turn them back on. So I'm going to move right about here to begin with. And at this particular spot, I'm actually now around the corner. I can no longer see the motion detector or the sensor over there on the wall. So I will make just a little bit of movement and again, successfully detected motion. So that's a good sign. Now I'm going to go back here and stand in the corner where I would normally be standing if I'm out here doing some work. Okay, I've let the motion clear. So now I'm just going to make a little bit of movement, and you can see, again, motion is immediately detected. And again, it's detecting motion with relatively small movements. So, you know, the good news is if I'm standing here and I'm working, unless I'm standing perfectly still for, 45 seconds or more, the new PIR sensor ought to be able to detect motion and keep the lights on when I'm out here working. So we've definitely improved on motion. What about our temperature and humidity sensor? Well, I've just brought these two external devices in from different parts of the house and hung them out here next to this. So we'll give them about an hour to stabilize and see if we're still in close agreement with our new AHT20 sensor. So after about an hour, I did go back out and took readings off the two external devices. You see they're both about 75.5 degrees Fahrenheit, 47% humidity. At the same time, the new AHT20 was showing right at 75.5 degrees Fahrenheit and 47% humidity. So we've definitely increased the accuracy of the temperature and humidity readings over the DHT22. So I do think that by upgrading my multi-sensor, I have been able to resolve the issues with motion and also improve the temperature and humidity readings. And the overall cost of the new multi-sensor was really about a wash as compared to the old one. And since none of the old parts were soldered together, I can actually take those parts out and reuse them for later projects. If you found anything in this video that you liked or found helpful, do me a favor and hit that like button. That lets both me and YouTube know you'd like to see more videos like this. And if you would like to see more of my content, consider hitting that subscribe button and ding that little bell icon if you want to be notified when I release new videos. As always, I'd like to say thank you for watching, and I hope to see you soon.